70 miles from the first shot of Operation Castle. A device with 1,000 times the energy of the bomb that shattered Hiroshima, exceeding the power of that bomb as vastly as it exceeded the greatest high-explosive giants of World War II. Multi-megaton weapons are here, stockpile items as of today, with potentialities that compel revision of previous military concepts. But without full knowledge of those potentialities, intelligent revision is impossible. To gain such knowledge, the Armed Forces Special Weapons Project conducted extensive military effects tests for the three services during Castle. The data obtained will serve as factual tools to shape our strategic and tactical planning to warfare's new dimensions, a transition which will take us from the familiar ground of low-yield capabilities into an era of new problems as well as new power. Castle was a two-atoll operation because the program was too big and the devices too powerful for convenient staging at a single atoll as in the past. 5 of the 6 Castle shots were fired at Bikini Atoll, 2 near Namu Island, 2 on barges in the north side of the lagoon, and 1 shot down on Inanman Island. At Eniwetok Atoll, some 200 miles to the west, only 1 shot was fired, number 6, on a barge in the old Ivy Mike crater. Ground space in the Pacific Proving Grounds is scanty in the form of small islands, and many of Castle's projects were handicapped by this fact. For one thing, it was not practical in most cases to lay out instrument lines involving runs over dry land alone for any sizable distances. It should also be remembered that all Castle shots, like Ivy Mike, were surface bursts. 2 of them fired in ground surface cabs, and the other 4 fired on barges. We therefore do not as yet have any empirical data on effects of multi-megaton air bursts. Looking now at the data we did obtain, we may first consider the nuclear radiation aspects. Initial gamma measurements on this operation employed orthodox techniques with chemical and film dosimeters and scintillation detectors at a number of island and reef stations. These studies confirmed Ivy Mike's indications that initial gamma from a high-yield device differs considerably in delivery timing from that of a weapon in the kiloton range. Roughly 50% of the initial gamma dose from kiloton weapons arrives within the first half-second after the burst, allowing no time for target personnel to take cover. With a multi-megaton bomb, however, some 80 or 90% of initial gamma will not arrive on target until after arrival of the shock front. At fair distances, this could provide a number of seconds for target personnel to take such cover as may be available. This timing differential becomes of academic interest only in view of another Castle finding. It developed that initial gamma dosage at ranges of concern reached only about 1/10 of the predicted levels. This means that initial gamma from the big weapons drops off to military unimportance at ranges at which blast and thermal will still cause almost 100% casualties outside of heavy bunkers. Measurement of neutron spectrum and flux were made indirectly by study of nuclear changes in threshold detector elements exposed on sample mounts at various distances. It developed that the neutron flux, while heavy, attenuated so rapidly with distance that in comparison to other effects, it too may be considered to have little military value. We come next to a field in which the radiological effects of megaton surface bursts are far from negligible, are, in fact, of profound importance. Ever since the 1 kiloton surface burst of Jangle in Nevada, we have recognized that such bursts may produce widespread residual contamination of significant intensity. Limited investigation on Ivy gave us scanty data, so our biggest Castle project was in this area. Further knowledge was a military necessity as well as grimly relevant to the defense of American cities. It is worth emphasis that only surface or subsurface bursts produce important fallout, and for the moment we will consider only land surface bursts reasonably approximated by the first Castle shot. The seawater involved in this fireball did not significantly alter the radiation levels or distribution of local fallout from what would be expected of a land surface burst. Fallout history begins with the scores of millions of tons of earth vaporized by such a detonation. This material, which rises with the fireball, has neither original nor induced radioactivity of any consequence. But during condensation, it traps radioactive bomb products significant for intense gamma emission. In the first few minutes, the visible cloud will reach from 60 to 100,000 feet or more for multi-megaton bursts with a stem over 5 miles in diameter. Fallout of the radioactive particles inside and below the visible structure now begins through the operation of gravity, rainout, convection, and other mechanisms. The active airborne particles move on downwind, causing significant fallout for a period of 10 hours or more. The settling dust reaches ground in a pattern which, while naturally quite variable, is reasonably represented as a long leaf shape. Starting back at the time of burst again, it is important to note that while the visible cloud will move with cloud height winds, the fallout particles will settle through lower winds of possibly conflicting directions at various heights. Orientation of the ground fallout pattern is determined by a resultant wind vector which is an average of all winds from ground to cloud height. Therefore, the fallout pattern may take an entirely different path from that of the visible cloud. Changes in the average wind vector as the falling dust moves across country can cause major distortion of the fallout pattern. The most important collectors of Castle fallout data were of two main types: total collectors, such as the gum paper trays and funnels of several sizes; intermittent collectors, such as belt samplers; and the rotating drums, both of which exposed collection trays at timed intervals. Such instrumentation in varying combinations was placed on a number of islands at Bikini and more distant atolls. Since this constituted scanty coverage, 26 instrumented stations were located on anchored rafts a few miles apart throughout the Bikini Lagoon. Losses of this type of equipment were heavy on the unexpectedly powerful first shot, which only 12 of the 26 stations survived. All those within a 10-mile radius were overturned. For the final shot, number 6 in the old Mike crater, a similar grid of 32 of these raft stations was employed to document the Eniwetok Lagoon. To extend the coverage outside the lagoons, original planning called for the use of floating band buoys in concentric rings at 30 to 100 miles from ground zero. They were instrumented with funnel and sticky paper collectors, plus small radio transmitters to assist in locating them after each shot. Success of the band buoy project was limited by difficulty of recovery due to high seas and change of shot schedules. On the last two shots, open ocean fallout was documented by a new technique of water survey and sampling methods. 1-gallon water samples were taken at a number of stations in contaminated areas at various depths from the surface to several hundred meters down. Further data were obtained from surface and underwater gamma meters, either lowered straight down for determination of radiation versus depth, or towed behind ships for contour surveys. Vertical profile data from the meters and from analysis of the water samples indicated that the radioactive debris mixes rapidly and uniformly throughout the surface layer down to the thermocline at around 120 meters. This vertical mixing information made it possible to estimate total fallout intensity at a given ocean site by measuring the activity of a single sample of surface water from that spot. All computations were correlated with the data from buoy and raft stations, ships, and island weather stations. In fact, emphasis on this open ocean survey resulted directly from the unforeseen fallout from Shot 1 on some populated distant islands, a weather station on one of them. These islands, functioning as accidental total fallout collectors, gave us our first real clues to the vast area affected by contamination from a high-yield surface burst. Within a few hours after that shot, a powdery snow-like fallout began on Ilinganai and Rongelap atolls, then on Rongerik, and finally on Uterik. By H plus 78 hours, 229 Marshall Islanders and 28 American service personnel were evacuated to Kwajalein for survey and treatment. It was tentatively estimated that the total gamma dose may have approached 70 Roentgens for the people on Ilinganai, 175 Roentgens for some on southern Rongelap, 80 on Rongerik, and only 14 on Uterik. The dosages in these outer fringe areas did not appear to reach levels of immediate combat significance, nor did any severely incapacitating effects show up during treatment or observation on quasulane in excess of 40 days. A majority of those receiving the heaviest radiation reported some transient nausea on the first or second day, and there was a small incidence of gastrointestinal disturbances of short duration. Some loss of hair was a frequent symptom. Most of the Marshallese in this category developed multiple skin lesions, usually not severe, predominantly on the scalp, back of the neck, and feet. Only a few developed mild secondary infections during healing. The lesions appeared to be directly related to the amount of fallout deposited on the skin rather than to the generalized whole-body radiation. It appeared that even one layer of clothing afforded substantial skin protection, suggesting that the beta energies of the fallout material were relatively low. Significant blood changes were found in patients from the heavier fallout areas, including pronounced lowering of both platelet and leukocyte counts, which would reduce the body's ability to combat hemorrhage or infection. Returns to normal were not complete after 6 weeks. Subsequent surveys of the fallout islands, together with autopsies of domestic animals, have indicated that intake of contaminants through the lungs in cases of this sort will be negligible compared to the external radiation dose, and will probably be negligible in comparison with the intake with food and water unless these supplies are protected. Possibly some new Air Force equipment. We can now take another look at the fallout material that came down on Rongelap. The small portion of the cloud material destined for southern Rongelap, where the natives lived, was emitting gamma at the rate of about 130 roentgens per hour at H+1, or 1 hour after the shock. Decaying with time as it traveled another 4 hours downwind, the material was emitting perhaps 20 roentgens per hour and still decaying when it grounded at Rongelap, 100 miles from zero. By evacuation time at H+50 hours, the maximum accumulated dose at that point was around 175 roentgens, a mild sickness dose for less than 50% of exposed personnel. The activity increased rapidly toward the uninhabited north, however, and in 10 miles reached a mean lethal level for exposed humans on the order of 450 roentgens. On the atoll's upper islands, this H+5 to H+50 hour dosage ran from possibly 1,500 to 3,000 roentgens, well above the lethal human dose. We can plot a line of peak observed readings, but considering the average wind vector, the center line of the fallout was apparently still farther north. Mapping from a few established values, we can at least approximate the minimum fallout pattern. The contours are selected to represent accumulated dosage from arrival time to H+50 hours. The 450 Roentgen mean lethal dose appears to have enclosed an area exceeding 7,000 statute square miles, an area some 250 miles long, an area which on land could blanket large segments of population. And note that inside this 450 Roentgen border, the dose accumulated by H+50 hours climbs quickly to 100% lethal for exposed humans. On the defensive side, remember that the gamma intensity of fallout at H+7 hours has decayed to 1/10 what it was at H+1, and by H+48 hours, it is only 1/100th of the H+1 value. Additionally, the shelter of a frame dwelling will cut the dose rate to 1/2 of the outside rate, and the position in the basement would reduce it to 1/10. Attenuations in excess of 1,000 can be gained in basements or middle stories of multi-story buildings or in simple shelters with at least 3 feet of earth overhead. In general, however, it should be recognized that the best average shelter available in cities will cut dose rates only to a level between 1/4 and 1/8 of the full dose. Immediate evacuation when fallout begins is not too promising, both because of sheer physical difficulties and because of probable lack of data as to safe and dangerous areas. The most practical solution appears to be the widespread use of available shelter for 2 to 4 days before attempting mass evacuation. We will consider now a phase of the fallout studies which was of major importance to naval operations. This was an experiment with a pair of modified Liberty ships to determine the effectiveness of a saltwater spray system designed to wash contamination from weather surfaces as a ship progresses through a heavy fallout area. Additional studies were made of the effectiveness of decks and other ship structures for shielding interior locations and of the entry of airborne contaminants through ventilation and boiler air systems. The Liberty ships designated as vehicles for these and related studies were YAG-39, fully equipped with a washdown system, and YAG-40 with no washdown. Each ship's modifications included a representative flight deck, 2 gun installations, and an F-4U aircraft carried aft. Both ships were heavily instrumented to measure gamma dose rate and total dosage. On each of the 4 shots participated in, an average of 400 detector channels was in operation, transmitting data below decks to the recording rooms. Airborne and weather deck beta distribution studies were also accomplished. The ships were equipped with drone control systems for remote operation of engines, steering, and the washdown apparatus of YAG-39. During the first 2 shots, both ships were unmanned in their maneuvers into the fallout region and were controlled from a P-2V-5 aircraft with a secondary control center aboard the carrier Biroko. Their surface contamination to levels permitting immediate topside emergency action after leaving the fallout. No thermal military effects tests were scheduled on Castle, but measurements were made of the thermal spectrum, power versus time, and total energy. Power versus time graphs show that the main thermal pulse of a low-yield weapon arrives and is essentially completed inside of a couple of seconds. From a high-yield weapon, it takes some 3 seconds to reach the peak of the main pulse, which has a comparatively long duration. Therefore, quick dodging, even into light cover, would allow target personnel to escape most of the thermal effects. This slower delivery time also requires a scaling up of low-yield thermal damage criteria. Equivalent damage from a 1 megaton bomb requires twice as many calories per square centimeter. The needed increase approaches 350% for 15 megatons and probably still more for higher yields. But even with these handicaps, the thermal destructive range of megaton weapons is huge. slope at the chosen altitude of 35,000 feet. Instrumentation was extensive, primarily to measure thermal effects. A total of 43 thermocouples was installed at selected points in skin and supporting structure. Radiometers and calorimeters in the fuselage gave thermal time history and total input. Additional instruments included accelerometers, strain gauge bridges, pressure gauges, and numerous temp tapes attached to the skin. 6 cameras under the fuselage were aimed at zero to assist orientation calculations. A thermal shield was designed for attachment to the inside of the canopy of the aircraft to protect the pilot and co-pilot. For locating the test aircraft's flight positions, radar was supplemented by the accurate radist system, which used the heterodyning or phase relationships of radio signals from transmitters on the ground and on the aircraft. Participating on 5 of the shots, the B-47's flight pattern was selected to position it where it should receive the theoretical maximum allowable temperature rise, 370 degrees in the aileron skin. In practically every instance, the maximum skin temperature rise was substantially lower than predicted for the observed input, indicating that predictions of heat absorption and transfer and of cooling factors were conservative. Heat damage was, in all cases, minor, involving only some patches of blistered paint at various points. Because of the B-47's high escape speed, the highest overpressure recorded was around 1/3 of a pound, and the only blast damage 60 degrees, 65% of critical. Predictions, especially for thermal response, were again generally conservative, with some inconsistencies. One effect observed was an abrupt momentary rise in jet tailpipe temperatures above the normal 500 degrees Fahrenheit. This appears to be the result of choking of the jet exhaust by overpressure and material motion associated with shock wave passage. However, no jet turbine damage was observed. At blast arrival on several of the shots, the B-36 reciprocating engines momentarily dropped and then raised their speeds by several hundred RPM before returning to normal. This was due to the engine torque balance being upset by the increased density and the gust immediately behind the shock wave. Visible thermal damage included some slight skin buckling on the elevators where white enamel had peeled or blistered, plus scorched enamel on some other areas. Some unprotected sponge rubber was burned around the lower aft blisters, one of which also developed cracks from thermal and/or shock effects. Spotty blistering and blackening appeared on the radome. The highest overpressure reached the critical 0.8 of a pound level, with the average around 0.5 pound. Blast damage included characteristic sheet metal dishing of wings, bomb bay doors, lower turret and landing gear doors, spotty rivet failure, and severe crushing of the radome. The highest gust loadings were on shot 5, reaching 60 to 90% of design limit load at various critical stations. It is concluded that the B-36 can withstand the critical overpressure of 0.8 of a pound with some minor damage. However, with current delivery techniques, the B-36 delivering multi-megaton bombs will experience less than this overpressure. Another phase of the aircraft delivery problem was explored by planes fitted with gyro-stabilized cameras, which recorded time, azimuth, and tilt on a corner of their film. These aircraft, carefully positioned, took pictures of cloud rise and spread, primarily with near collapse of all lightly built structures. We will call this level moderate damage. A 100 kiloton weapon at optimum height will cause severe damage over an area of 5 square miles and moderate damage over 12 square miles. Contrast this, 5 and 12, with 80 square miles of severe damage and 240 square miles of moderate damage from a 15 megaton surface burst like Shot 1. 240 square miles, more than 20 Hiroshimas in a group, more than 10 Manhattans, in which blast compounded with fire may bring almost total destruction. An idea of the extensive damage that 15aircraft. The transducers or gauges were of several varieties: mechanical, electromechanical, and piezoelectric. The underwater pressures were of military interest from the standpoint of effects on ships, submarines, sub-pens, harbor facilities, minefields, and dams. The primary finding was that the pressures from a shallow water surface burst were about of the same magnitude as the air overpressures at the same distances, and are therefore probably of small military value. A related project was